vector operator? It looks like maybe. There's another rule we're about to come up with over there. All right, so this is specifically, I have this change in R, but in reality, we're dealing with 3 dimensions. I mean, you don't have to necessarily run straight along in one direction. The more generalized form of this is the electric field is equal to the negative nabla V. I guess, Ben, you were the one who thought maybe somewhere in the recesses of your mind, does that symbol look familiar to you?
Possibly, yeah.
Okay.
What it means, I'm not sure, but.
All right. The symbol is called nabla. It is a vector operator. Div grad curl, that ring a bell? I think this is Calgary stuff, but.
It's been a year for me, so.
What was that?
It's been a year. I don't remember
That symbol?
though.
Okay. This nabla, there are 3 major operations that you do with it. This is known as gradient. So this can also be written as negative grad V. There is the nabla dot something. This is, when you're doing a dot product with it, this is known as divergence, or div E. And if you do a cross product, this is known as a curl. If you ever have to deal with this, there's a book called Div Grad Curl and all that I would recommend. Probably gives the best, for me, it gave me the best conceptual understanding of this. I'll try to impart that.
I remember the gradient, but I don't remember the name nabla or any of those other.
Okay, partial derivatives?
Yeah.
Okay, partial derivatives are about to pop into it. If you haven't dealt with partial derivatives, the mechanics of it, incredibly simple. Simpler, it's easier than regular derivatives. All right, if I have a vector field cruising along like that, doesn't matter, in this case, if it's an electric field cruising along, the divergence is, if I have a surface here, the divergence is an indication of the number of electric field lines going in versus coming out. Divergence is positive if, I think, more out than in. It's negative if more in than out. Very much related to electric flux. Curl deals with, if I have an electric field cruising along like that, if I imagine, if these are, imagine it's water flowing. If I stick a paddle wheel into it, which way is that paddle wheel going to turn? Well, if I have just as much on this side as this side, in other words, my field is constant, it's not going to turn one way or the other. Curl is 0. If it has a tendency to curl, to turn this, then you have a curl. That's the essence of those. Oh, and gradient is basically a slope. Now, in rectangular coordinates, which is what we would deal with here, the nabla equals I hat del x. This del here, it's like a curl d. This is a partial derivative. Plus j hat del y plus k hat del z, assuming that I hat, j hat, k hat are in the x, y, z directions respectively. If I have V, if I have an electric potential that is equal to 4xy, so if I tell you the value of x and y, I got a coordinate system, I tell you the value of x and y, you can tell me what the electric potential is. If I plugged this into it, I'd have, if I wanted to find my electric field from this, that's equal to negative del V which is negative I hat del x v plus j hat del y v plus k hat del z v. I don't think it's officially called the distributive property, but in essence, that's where my nose goes on it. Partial derivatives, when you're doing a partial derivative, you assume that anything that is not the letter that you're taking the derivative of, with respect to is a constant. So 4xy, the partial derivative of 4xy with respect to x, well, x is the variable, 4y is considered a constant. So negative I hat times 4y plus j hat, the partial derivative of v with respect to y. Well, you consider x to be a constant now, and so this is 4x. Plus k hat, you now take the derivative with respect to z. There is no z, so that's 0. And so my electric field would be negative 4y I hat plus 4x j hat. Yep, sorry, the whole thing negative. We'll do one more and then connect this with some of the other stuff we're doing, come up with another rule here. If my electric potential can be described by the following formula, 3xy squared plus 2xz minus z cubed. If my electric potential can be described by that formula, what is my what's my I hat component?
4y squared plus 2z. Minus 3z squared.
Yep. And so we have an electric field. We have a mathematical relationship between the two. Now, most of the time we'll deal with cases that are much simpler than this, but there is a purpose to this, other than just the joy of doing it. All right, so the questions up to here before I can try to connect this. So if I look in the first quadrant and say I've got x and y, I know that my electric potential at at 1, that would be electric potential of 4 volts. So let's just assume it's going to be in volts. So at the point 1, 2, this will be 8. This will be 12, and so on. If I go up this axis, this also will be 8. That will be 12, and so on. If I try to connect all the points that have the exact same potential, I know that at 1, 3 and at 3, 1, it's the same at the point I guess that would be 16 if I did that one, so, well, there's gonna be a point somewhere in there, which also is at 12 volts. And I can sort of come up with, if I do enough of them, I come up with a general idea of what my 12 volt line looks like. My 8 volt line looks like this, my 4 volt line will look something like that. And that's supposed to be V. Now, first off, if I put a proton here, which way would it have a tendency to go? So, proton right here.
Left.
Not necessarily left, but towards the lower potentials. It probably would actually go in that direction. Let's actually figure out what this point is. So that point right there, when x and y are equal to each other, so this is 12 is equal to 4x squared or y squared, so x is square root of 3. So this is the point 1.7 something, 1.7 something. What is the electric field at that point? Well, we have a formula right here. The formula, -4 times square root of 3, I hat, minus 4 times the square root of 3, j hat. In which quadrant is that pointing? Towards which quadrant does that point? 3. Yeah. My electric field at this point right here is basically in that direction. Let's do one more. Let's take the point out here. If y is a half, x is 6, and so the point 6, 0.5. That should also give us 12 volts. So there's going to be a point out here. My electric field at the point 6.5, I got -4 times 0.5, so -2 I hat plus 24 j hat newtons per coulomb. That's sloppy there. Any questions about how I got those numbers? All right, so I'm out here, let's check out the direction of it. So it is -2 I hat, so basically to that direction, and then 24 that way. So in essence, the electric field is pointing in that direction. What do you notice about the electric field and the equipotential line?
It's perpendicular.
Yes, and that is another rule. Because the surface of a conductor in equistatic equilibrium, I feel like I said one of those words wrong. Surface of the sphere in electrostatic equilibrium, there we go, is equipotential. The electric field at the surface, of conductor in electrostatic equilibrium is perpendicular to the surface. And that's, well, it all ties together. But the gradient creates a vector perpendicular to the function, the slope. Left off, got that one, got that one. And actually, in general, I guess that's a corollary of the electric field is perpendicular to equipotential lines, surfaces. It depends upon what we're working with. Questions before I connect this with what you will do on Monday?
Lab 2
The-
on Monday.
On Monday, the lab you'll be doing on Monday. I view it as lab 3.
Oh.
What you did last week will count as a lab. Or this week, 2 days ago. So what you're gonna do is you're gonna get a sheet here that basically is conducting. You're gonna have a tack here, a tack. One's a negative, the other one's gonna be positive when you get into the meat of the experiment. Now, we cannot measure electric field lines, but we can measure equipotential lines. If I have this hooked up to a 12-volt battery, the symbol for a battery, for the purist, this is officially a power cell. I will still call it a battery. I've had probably one student who was scared. I don't know, maybe I have 2 now. But officially, a battery would be more than one of those. So a battery, the symbol, that would be a battery. That's just a power cell, but I'm still using that for battery. So I hook it up. I know that there should be 12 volts between the two. I got it hooked up to 12 volts. If I have, so I'm going to get a digital multimeter. I'm going to have a negative lead to here, and I'll have a positive lead somewhere. If I put my positive lead onto that, the digital multimeter will register 12 volts. In a nice ideal world, if I touch it to the middle, halfway between it, it should register 6 volts. Reality is, it usually is not, but it should be relatively close. So what you're going to do is you're going to measure the potential at some spot. Technically, the potential difference between these 2 points. And then you're going to try to find other points that have the exact same potential. So, again, in a nice ideal world, smack dab in the middle, there should be an equipotential line that runs perpendicular. Over here, there'll be equal potentials in sort of a curve, and depends on how far you go. Once we have our equipotential lines, we can then come up with the electric field lines, because I know the electric field lines are going to be perpendicular to these. It goes from positive to negative, it is perpendicular to those lines, so it should hit that at a perpendicular angle, perpendicular angle. My recommendation is when you first draw your electric field lines, do it lightly in pencil. And so your electric field lines should look something like that. And so that's the first part of the lab. And in the second part of the lab, actually, no, I'm doing the overback condition view. So you won't find the potential smack dab in the middle, but with an offset, because there's basically a track running underneath it, and you can easily put holes in the paper. And I'd like to avoid that as much as possible. So you go slightly off center, and then find other points that have the same potential. And then I'll give you, in theory, a mystery one for you to figure out what the configuration is based upon the equipotential lines. Questions? Up to here. PJ's packing up, so I guess it's time to go.